Hello, everyone. Welcome to a new Learn and Share session. I'm Vivian Plasencia, and today we have Shengru and Jens, who will be talking about zero-knowledge location privacy. As usual, you can write the questions in the chat, and Shengru and Jens will answer all of them at the end of the presentation. You can also unmute yourself at the end of the presentation to ask questions. Welcome, Shengru and Jens, and thank you so much for being here, and the stage is yours. Feel free to start when you want.
Okay, so let me share the screen. Okay, so thank you, Vivian, for introducing us, and we feel pleasure to be able to present our work on zero-knowledge location privacy at PSE's Learn and Share. So So today we are going to present our work zero-knowledge location privacy while accurate floating point snarks. And this work is done by Jens Luca and Sebastian from TUM, and Philip from UCL, and me from HKU. So let's get started. So nowadays, location-based services are ubiquitous. So there are a lot of geolocation-enabled devices like tracking devices, for example, Tile or AirTag, and mobile phones mobile devices like smartphones and vehicles. So the data collected by these devices are sometimes open source, for example, in OpenStreetMap, which provides open source mapping data, and OpenCellID for wireless data. New York City also open sourced their taxi data. And these data are used for spatial data processing and analysis in services like Uber Eats and Airbnb and Snowflake Marketplace, which is a platform where you can share your data or purchase third parties' data. However, for these services to work, you always have to give your exact location, which often leads to mishandling of data. For example, in the taxi data open sourced by New York City, their anonymization technique has a flaw that leads to the privacy leak. For example, people may learn your behavior or the place you visit. The core problem of their anonymization technique is that they simply hash the taxi's license number and the taxi's ID, but without source. So researchers can simply brute force the search all pre-images of the hash and infer which pre-image the digest corresponds to. Yeah. So in this work, we study the problem whether we can develop a solution that provides location obfuscation while without ever disclosing the actual location. So our idea is to prove location is bounded by a hexagon in zero knowledge without leaking the exact position of the prover. So why hexagons? Well, hexagons provide a lot of great geometric properties. For example, it can tessellate a plane without gaps. It has rotational or reflectional symmetry, and the distances between its center and all its vertices are equal. And hexagons are actually used in icosahedral Goldberg polyhedrons, which it uses hexagons for perfect tessellation of a sphere with extra 12 pentagons to cover the sphere. So a real world example is a soccer ball, is the classical design of a soccer ball, which has 12 black tiles for pentagons and 20 white tiles for hexagons. And this icosahedral Goldberg polyhedron is actually used in the industry. For example, Uber H3, the index system proposed by Uber assigns 3D coordinates to each hexagonal cell, and the hexagon actually provides various solution from 1 square meter to 4 million square kilometer. Yeah. And to apply the Uber H3 index system in our zero knowledge proof, there is a problem that we need to tackle. That is, how can we retain accuracy towards hexagon boundaries? The major challenges are twofold. First, the hexagons can be either very small or very large. And second, mapping a coordinate to the index in Uber H3 requires trigonometric functions. So these challenges leads to the solution that we use a data type that supports both representing both small and large values, as well as allowing for complex operations like geometric functions. So this data type is floating point numbers. So in floating point numbers, there are basically two formats, the base 10 formats called decimal formats and the base 2 one called binary formats. And today we are going to talk about binary formats, and examples of them are single precision floating point values and double for double precision floating point values, etc. And in these binary formats, we always have 1-bit sign S, but the length of the exponent and mantissa can vary. For example, there are for the single precision floating point value, the length of exponent E is 8, while the length of the exponent for double is 11. And for mantissa, the single precision floating point value has 23 bits, while for double, it has 52 bits. And generally, a real number or a normal real number is expressed by this equation. The sign, if the sign is 0, then alpha is positive, while if the sign is 1, then alpha is negative. And the exponent is actually biased, means that we need to minus 2 to the power of e minus 1 plus 1 to get the real exponent. And in the mantissa, there is it's an explicit leading 1 that is omitted in the encoding. So the sign, the biased exponent, and the mantissa with implicit leading 1 compromise the entire real number. So why we need to use floating point number? We know there is another format for encoding real numbers in computers, which is fixed point. In fixed point numbers, for example, we consider a format with 16-bit whole number and 16-bit fractional. That is, the fractional part is always fixed with length 16 bits, and the mantissa part is also fixed with 16 bits. And such a floating fixed point number can have range from -3 to 1,000 to plus 32,000 with precision 0.00015. However, although these fixed point numbers have better performance in hardware, they often needs a lot more space to store than floating point numbers. On the other hand, for example, we can use only 16-bit floating point numbers to represent values with similar precision and ranges, or even larger ranges. So such a floating point number, 16-bit floating point number, as we have talked before, can be split into three parts: the sign part, the exponent part, and the mantissa part. And such a encoding maps to the real number, this one. So the exponent actually has a bias. So it's actually 5 instead of 11100, which is 30 16 plus 4, which is 20. So it has a bias of -15. Yeah. And the mantissa has a leading 0, so it's actually 1 point, the encoded value. Yeah. So this binary string actually encodes 54.16. Okay, so another problem is why we need an accurate floating point in snarks. So in fact, arithmetic errors can cause detrimental effect. For example, in so in the Ariane flight V88, there is an accident that when people converts floating point numbers to integers, there are some accuracy loss that prevents the rocket from flying normally and causing the disaster in the rocket. Yeah. So our goal is to propose a method that allows for accurate floating point numbers with well tested against present standards like IEEE 754. So let's see how can we achieve this in snarks. But before that, we we briefly introduce how floating point arithmetic is done in modern hardware. So generally, there are 5 steps in a basic floating point operation. First is to compute the exponent, which depends on the actual operation. But for example, for addition and subtraction, the resulting exponent is the maximum value of both. And for multiplication or division, the resulting exponent is the sum or difference of these two. And the next step is to compute the mantissa part, which is actually also depends on the actual operation we are interested in. So for addition and subtraction, the mantissa is also the mantissa, the addition and subtraction of the corresponding mantissas, and this is also the case for multiplication and division. And the third step is to normalize the mantissa. That is, for a mantissa who is too small, like whose length is smaller than m, we need to left shift m until its length is big M, while we decrement e by the corresponding offset. And for mantissa, which is too large, whose length is larger than m, then we on the other hand right shift m until the length equals m's length equals big M, and we increment e at the same time. So the fourth step is rounding. That is, we round the final mantissa according to some rules. And in IEEE 754, the default rounding rule is to round to nearest while ties to even. That is, for 0.1, 0 is the nearest number, while for 0.81 is the nearest. While for 0.5 and 1.5, we always maps them to the nearest even number. That is, 0.5 maps to 0, while the rounding result of 1.5 is 2 instead of 1, because 2 is an even number while 1 isn't. And the rounding direction is actually determined by 3 bits: the guard bit, the round bit, and the sticky bit. So in IEEE 754, the guard bit and the round bit are both the guard bit G and the round bit R are important because there might be some accuracy loss and the resulting mantissa might have less precision than the original, which which may cause some accuracy loss in the final result if we only have one of G and R. So both of them are important. However, in our application, we keep the accurate intermediate mantissa, so we don't really need both of these bits. We only need one and the sticky bits. Yep. So the final direction is computed by G and P or R or S. That is, if G is 1 and there are some non-zero bits in the round bit or the sticky bit, then we need to add the intermediate mantissa by 1. While if G is 1 and round is 0 and all following bits are 0, then the rounding direction depends on the parity P. If the parity is 1, if the intermediate mantissa is 1, then we need to add 1, while if the intermediate mantissa is already odd, is already even, then we don't need to add 1. And on the other hand, if the guard bit G is 0, then the following bits are smaller than 1 1 0 0 0, and so we don't need to add 1 into the final mantissa. Yeah. And finally, we need to handle some edge cases like division by 0 or overflow or underflow, etc. And now let's get into more details of floating point numbers. So first we consider how a floating point number an encoding of the floating point number maps to the real number. If the exponent is exponent e is 0, then there are two cases where if the mantissa m is also 0, then it maps to plus or minus 0, while if the mantissa m is non-zero, then it maps to subnormal numbers, which is actually written by this. And for a non-zero exponent e, which is smaller than this 2 to the e minus 1, then the resulting real number is called normal numbers. And finally, there are two weird cases where e is equal to the big E minus 1, and then we say the real number is infinities if the mantissa part is all zeros, while the real number is so-called not numbers or nans if the mantissa part is non-zero. So in order to handle all these cases while compute the floating point operations that are compliant to the standard, we first introduce some general optimizations in circuit, and then we discuss our tailored optimizations for floating point. So first, a common technique used in snark circuit to improve efficiency is the non-deterministic advice, or so-called hints, which instead of execute the original computation inside the circuit, we ask the prover to provide some hints to the circuit, and the circuit can track the correctness of these hints in a more efficient way than the original computation. So for example, if we compute alpha over beta, the division between alpha and beta, instead of computing the division of this mantissa in circuit, we ask the prover to feed the quotient Q and the remainder R as hints, and then the circuit only needs to enforce the mantissa of alpha equals Q times beta's mantissa plus R, and as well as the well-formedness of Q and R. Another example is the computation of square root of a floating point number alpha. So again, instead of computing the mantissa of alpha in circuit, we also ask the prover to feed the square root n as a hint, and then the circuit only needs to enforce the square of n is smaller than alpha's mantissa, which is also smaller than n plus 1, the square of n plus 1. Yeah, this track is actually sufficient because there is only one square, one number that satisfies this track, which is the correct square root number of alpha's mantissa. And another technique that in recent years is via lookup arguments. So for example, if we want to track if the value v is in the range from 0 to the power of big V, where big V is a constant, then we ask the prover to feed v0 V1, etc. as hints, and the circuit enforces that V is indeed the concatenation of these so-called limbs of V, and then the circuit also enforces that V0, V1, all these limbs are in a pre-computed lookup table via lookup argument. In fact, if V0, V1, and etc. are all bits, then this method is in fact the traditional bit decomposition technique. While if the length of V0, V1 is larger than 1, then we can handle this more efficiently by building a larger lookup table. However, this range check becomes more expensive when the range bound of the value V is a variable. In our case, we always consider the upper bound of this value V also has a upper bound, which is 2 to the power of big U. So to do a variable-sized range check, we in fact decompose this check into two. That is, we first enforce V is smaller than 2 to the power of U, but greater than or equal to 0. And then we also enforce U minus V minus 1 is greater than or equal to 0, while smaller than 2 to the power of U. So as we can see, the variable-sized range check costs twice as much as constant-sized range checks. Now, let's discuss the integer operations. So we are majorly interested in two operations. First is the computation of the absolute value of x, and second is the right shift operation on x. So to compute the absolute value of x, we first need to define the sign of x, because all these variables in a circuit are in a finite field, but there is no sign in these field elements. So we manually divide the finite field into two parts. So we say the sign of x is 1 or x is positive if x is in this range from 1 to p minus 1 over 2. And on the other hand, we say x is 0, the sign s of x is 0 or x is negative if x lies in the range from p plus 1 over 2 to p minus 1. So by doing so, we are able to determine whether x is positive or negative. And to achieve this in an arithmetic circuit, we also leverage the non-deterministic feature, the non-deterministic nature of arithmetic circuits. So we ask the prover to provide the sign s as a hint, and then compute the absolute value depends on s, which is if s is 1, then x is positive, while if s is 0, then x is negative. So we compute the opposite number of this x. Then the circuit enforces that s is indeed a bit, is indeed either 0 or 1, and we check if the absolute value is in this range between 0 and 2 to the power of L. So if the prover provides a fake as an incorrect as, then the absolute value would be negative, and such a negative value cannot fit in this range because here L is reasonably small than the log 2 of this field order. And finally, the circuit simply returns S as the sign and the absolute value. And now let's see how we improve the computation of right shift. So here we also assume that the X has upper bound 2 to the power of L and D has upper bound K. So let's compare the left-hand side with the right-hand side. So intuitively, we can ask the prover to provide the quotient Q and the remainder R as hint for this division operation, and we enforce the Q and R are well formed, and we also enforces Q and R can recover the original X by comparing X with Q times 2 to the D plus R, and finally return Q and R. However, as we have discussed before, this D is in fact a variable, so the upper bound of R is also a variable, and this track is in fact pretty expensive. So in order to get avoid of this variable-sized range track, we instead ask the prover to provide hints QR for the operation x times 2 to the power of k minus d over 2 to the power of k. So in this case, the divisor 2 to the power of k is a constant. So when we check the range of R, we are comparing it with 0 and 2 to the power of k, the divisor. So this becomes a constant sized range check, which is in fact twice as effective as this variable sized range check. Then we simply compute x times 2 to the power of k minus d and compare it with q times 2 to the power of k plus r, and returns q as the result and r as the remainder. Okay, so then let me introduce how we introduce optimizations tailored for our floating point operations. So first, we convert the IEEE 754 representation to a circuit efficient form. First, we treat subnormal numbers as normal numbers to avoid handling these values separately. So this is done by shifting the mantissa to the left by d minus 1 bits, so that all zeros are shifted out in subnormal numbers, while the 1 becomes the implicit leading bit. At the same time, we also decrement the exponent by by d minus 1. So the original exponent is 0 for subnormal numbers, and the resulting 1 in our circuit becomes 1 minus d. And we also mark this 1 as implicit because this is the case in normal numbers. However, we can although these subnormal numbers behave similarly in normal operations, one pitfall is that in rounding we need to take care of these subnormal numbers because they have lower precision than normal ones. And we will introduce this later. Yeah. So for for a normal number, we also expand its exponent and mantissa to simplify computation. That is, for a normal number with e and m as its exponent and mantissa, we compute the unbiased form of exponent, and we also compute the mantissa with its explicit leading one. Finally, we also unify all NaN values by using a canonical NaN. However, this doesn't allow some techniques like NaN boxing, but overall people don't really do this complicated techniques. We only treat NaN um as a abnormal value, so it's it makes sense to do this unification. Yeah, so because nans and zeros behave similarly in multiplication, we simply set the mantissa of these nan values to 0, so they can share some computation in multiplication with zeros, and in turn can save some constraints in our circuits. And let's talk about bit operations for rounding. So as we discussed before, subnormal numbers is treated as normal numbers. However, it actually has lower precision. So in rounding, we need to preserve less number of bits than normal numbers for subnormal values. Yeah. So this leads to our design of configurable mantissa length. That is, we keep m+1 bits for normal, but m+1 minus delta E bits for subnormal, where this delta E is a parameter that controls how many bits to keep for subnormal numbers. And the second technique we apply is to split the intermediate mantissa to compute the rounding direction more efficiently. So here, we instead of handling this guard bit, round bit, and sticky bit separately, we first only need one of this guard bit and round bit. So we only need round bit, and then to compute this sticky bit, we don't really need to compute the logical OR of all of these following bits. We can simply keep all these values, these following bits, and compare S with 0, because computing logical OR in circuit is costs one constraints for each operations. So there are a lot of bits here, and the overall cost is pretty high, while comparing a value with another value only takes two constraints. Yeah. And so instead of computing G, logical AND P or R or S, we now compute R and P or S equals 0. Yeah, and back to our technique for splitting the intermediate mantissa into 4 parts: the M prime part, the parity part, the round bit part, and the S part for all bits in this sticky bit computation. So we first need to avoid a variable-sized range check on this S, because the resulting M may be smaller than this M plus 1, but can be instead M plus 1 minus delta E, where delta E is a variable. So we need to compute the resulting S with a variable-sized range check. But as we have mentioned before, the variable-sized range check is expensive, so we need to apply some techniques that that we mentioned before, which is to left shift the mantissa the entire mantissa before splitting, and then we simply make this S, the length of this S, constant to save some constraints. And finally, we determine the rounding direction by removing the guard bit and removing the logical OR in the computation of this sticky bit. So yeah, as I just talked about, we remove the guard bit and simply assume the intermediate M has sufficient precision, while we get rid of this logical OR in a sticky bit by simply comparing S with 0. And finally, we talk about 2 examples for floating point circuits, which is the multiplication and the computation of square root. So to multiply 2 floating point values alpha and beta, we first add their exponent as I talked about as I talked earlier, and then we multiply the mantissas to get the intermediate mantissa, which is M equals the product of alphas M and betas M, and M is either 0 or lies in the range from 2 to the power of 2M to the power of 2M plus 2, because the M of alpha and beta are either 0 or in 2 to the power of M and 2 to the power of M plus 1. So the resulting M is in this range. And by observing that the range of M, we can in fact simplify the normalization process. That is, we only need to receive a single bit from the prover as a hint, which is the MSB, that is the 2M plus 1 bit of M. And this is because M now only the M now has 2M or 2M plus 1 bits. So there are only 2 cases for a non-zero M. So we only need to left shift the intermediate M by 1 if its MSB is 0, but if a non-zero the MSB of a non-zero M is 1, then no shift happens. So these are the only two cases. Yeah, so providing a single bit m is sufficient for our normalization. And the circuit then enforces this b is a Boolean value and enforces that b minus b times 2 to the power of m plus 1, that is m without the leading bit m, leading bit b is in the range of 0 to 2 to the power of 2m plus 1. And finally, we compute the normal mantissa as m left shift by 1 minus b, and the resulting exponent, which is e plus b. Next, we round the intermediate mantissa by adding this value as described before. And finally, we handle some edge cases like the multiplication between a normal value and infinities, or the multiplication of zeros and infinities, which produces nans. And yeah, that's all for multiplication. And for the square root of alpha, we first help the exponent by left shift the exponent of alpha by 1, and we obtain the tentative exponent e and the bit 1 the bit b, which is the shifted out bit. Yeah, and then we compute the square root of the mantissa of alpha. So again, we ask the prover to provide a hint for the square root operation, and we enforce the range of the range of this original mantissa is between the square of n and the square of n plus 1. So however, in our case, we need to shift the original mantissa before computing the square root, as the original mantissa only has big M bits of precision, and after taking the square root, the precision becomes m over 2, which is too small for a desired precision value. So we need to first shift it to the left by m plus 4 bits to make sure that the resulting n is accurate enough. And we also add the bit b to double the original mantissa when this original exponent is odd before the shifting operation. And we can even avoid this normalization process by observing that the MSB of a non-zero and the square root is always 1, so we don't really need to left shift or right shift the intermediate mantissa. However, in rounding, we need to be careful because the square root may require infinite bits of storage. However, our n only has about big M bits. So we introduce some auxiliary information to help determine the sticky bit. That is, if the shifted mantissa is a perfect square, then n is followed by all zeros, so the sticky bit should be 0. And otherwise, the following bit should contain some ones, so the sticky bit should be 1. And this logic converts to the blue part, which additionally compute the logical AND between s equals 0 and the equality between n squared and the shifted mantissa. Finally, we compute the we handle the edge cases. For example, the square root of a negative number is there is no square root of a negative number, so we simply return nonce. However, for -0, the specification defines that its square root is -0, so we need to return -0 in this case. Yeah, so that's all of my part, and then let's invite Jens to talk about our ZKLP circuit with our tailored optimizations.
Oh, great. Let me share this. There you go. Okay, great. Thank you, Chengru. Yeah, great. So now that you've seen basically how we represent floating point values in circuits in kind of like an adapted, optimized way, and how we do multiplication and compute square roots, we can basically use this in applications, right? So in addition to square root and multiplication, we also have circuits for addition, subtraction, and division. You can find the details in the paper, I guess, and I'll just describe the application that we basically use the floating point circuits for. Right. So Chengru already introduced basically the Uber H3 algorithm, just to recall how that essentially worked. So you can see on the top right, you have the icosahedron, right, which is the top leftmost picture, and then you basically map that onto the sphere of the Earth and then project basically hexagons into each of the icosahedrons, right, in kind of like the Goldberg polyhedron formation. And on the left, you see basically the latitude and longitude mapping to an index of each hexagon that is employed in the Uber H3 algorithm. Okay, so the input basically to this algorithm is the latitude and the longitude and the resolution. The resolution is from 1 to 15. So if you have a resolution of 1, each hexagon covers like an area of like 1,000 square kilometers. Whereas if you have a resolution of 15, the area that an hexagon covers is 1 square meter, roughly. So what you do is essentially in this algorithm, you convert the latitude and longitudes to radians, then you convert it to spherical coordinates, the spherical coordinates to Cartesian coordinates, XYZ. Then for each of the triangular, basically, icosahedron faces, you calculate the closest distance and choose basically the icosahedron with the minimal Euclidean distance to the actual latitude and longitude, or XYZ coordinates in this case, right? Then you calculate the radial distance based on the resolution as well. Then you convert that basically in the end to 2D Cartesian coordinates and map that to a 3-dimensional coordinate system that uniquely identifies each hexagon that is mapped onto the sphere, right? Uber H3 afterwards also maps that to basically an index in hex format. We don't do that because IJK coordinates are already sufficient to identify a unique hexagon on the sphere, basically. Right. So what's the actual problem with this? Turns out that this transformation, this spherical transformation from latitude, longitude to index involves a lot of trigonometric operations, right? So first one being x, y, and z. So the three-dimensional Cartesian coordinates are calculated from through applying sine and cosine, basically, to the input latitude and longitudes, right? Which is kind of like the first problem, and then afterwards you apply a lot more trigonometric transformations, such that you finally basically end up with the IJK coordinates, right? I guess on a high level, it's the only thing you need to know. So what we do is we essentially apply two optimizations, right? First one is we eliminate the first trigonometric function in the beginning, right, by replacing basically the x, y, and z coordinates that are usually computed directly by sine and cosine with a computation through hints, right? So we compute the trigonometric functions out of circuits and then use the relation between the trigonometric functions, right, the trigonometric identities, to check in circuits that the provided values are actually what we want them to be, right? So then we basically get rid of the first trigonometric function that we need to compute in circuit, and afterwards, as you saw here, right, like everything besides the first black box is basically the rest that you need to do in circuit. It turns out, if you think about it long enough, you can figure out how to use trigonometric identities to end up with an optimized version that only uses basically a square root instead of trigonometric functions themselves, right? So what you can see in on the right side is the optimized function. So you see R, for example, is not computed from any trigonometric function, just uses square root and exponentiation, right? And x and y similarly, where you can see that the cosinus of theta fi, that is a constant, for example. So all of the values, the cosinus, sine, cosine, sine, and whatever you see on the right side in x and y are all constants, right? So, right, those are basically the optimizations that we have on this side. Then we basically implemented we implemented everything, right? We use to test the floating point implementation, the Berkeley TestFlow 3 repository, which provides a set of test cases that ensures compliance with the IEEE standard. Then we apply basically all of the floating point operations in a way that enables us to prove the latitude longitudes to index transformation and double check that our implementation is equivalent with the one of Uber by using the Uber code to essentially directly spit out the transformations for different sets of latitudes, longitudes, and hexagonal indices. And we do the testing in a way, as you remember in the beginning, we said we need floating point operations to basically determine, to retain accuracy towards hexagonal boundaries, right? So what you can see on the bottom here is we tested this against an unoptimized fixed point implementation that uses fairly naive implementations for cosine and sine. And as you can see, for example, for a fixed point implementation with 6 digits after the comma, basically our tests already fail for the middle of resolution 11. So for example, for resolution 11, we have like 10 test cases, and each test case is logarithmically closer to the boundary. So we kind of like logarithmically approach the boundary of a hexagon for each of the resolutions. As you can see, for 6 digits after the comma, it already fails for resolution 11, and for FP32, it only fails for the end of resolution 15, and for FP64, it basically passes everywhere. Right. Now to the evaluation. So how performant are our circuits actually? For the floating point implementation, what you can see on the top right is basically the R1CS constraints that you need for a table size of the lookup table of 2 to the power of 8. Those are divided in basically native constraints, which is everything besides kind of like the lookup argument. In this case, that is 31 plus like the 33, which are basically the number of lookup constraints per multiplication that is scaling linear with the number of multiplications. And the 291 in this case would be fixed, right, for FP32. So the interesting thing here for the lookup argument, what you get is amortization, right? So in the lookup argument, what you have is you have a set of queries, and then you have a set of table entries, which is basically a vector that describes the table. And you can see the equation that is used to check that the lookup argument is actually correct, which is derived from the lookup work of Ulrich Habeck. This equation is actually checked in circuit, and you can see that basically the right side that computes, so the constraints that compute the right hand side of the equation are constant, as well as checking the equality is constant, right? So those end to like an amortization in the overall number of constraints that you need if you have like a certain number of multiplications that is larger, right? So for example, you can see in the bottom right, you have 2 to the power of 15, 2 to the power of 15 floating point multiplications in a circuit. You'll see that it ends up approaching basically 64 constraints per multiplication, right? Which is equivalent to what table 1 says for an FP32 multiplication operation. Right, so how does that impact our zero-knowledge location privacy circuit? The zero-knowledge location privacy circuits is fairly performant. So for FP32, it only has around 20,000 constraints. Just to set that into comparison, the baseline that we use to evaluate fixed point operations with like a naive implementation for sine, cosine, and whatever, that uses 310,000 constraints, right? So this implements basically the exact Uber H3 algorithm without optimizations and with naive fixed point implementation, which should have theoretically less constraints because it's not as complex as floating point computation. Right, and we also apply this to basically another application that is P2P proximity testing. So once you have like a proof that proves that you're inside some kind of like hexagon, you can out of circuit just determine the distance to the closest point on the boundary of the hexagonal index. And that plus the verification of proof allows any peer to evaluate basically proximity to greater than 400 peers per second. Right, if you noticed, then there might be one problem that still arises, and that is that of authentic locations. There is a couple of approaches that you can use here. Ideally, you have signed GPS signals, but that also like is kind of like suboptimal because then you can still forward the signed GPS signal to some peer. There's other approaches that use kind of like a Byzantine network to basically triangulates the location of specific devices. Here, the problem is that you end up with like a very high inaccuracy. I think the lowest that you can get to, I mean, that depends on the kind of like number of challengers that you have in the network, but I think approximately if you have like, I think there was a paper recently that describes this. If you have like 100, you get down to like 100 kilometers of accuracy. Which doesn't allow you to go down to resolutions of like, I don't know, a square meter, right? And yeah, for that you also need very accurate timing information because if you basically do triangulation based on like round trip time RTT, then yeah, you basically end up with a very large disappearance based on the speed of light. Right, so ideally you use like a secure enclave that just attests to whatever location you're in. Problem here is if you look at an iPhone, for example, secure enclave doesn't provide attestation to location information. So you would have to find some kind of like workaround, I guess, maybe through like trusted execution environment with kind of like universal programmability. Yeah. Right, and if that is a given, you can do very fun things, as we already built with this hexagonal index. You can apply arbitrary algorithms. For example, like Uber is using this to calculate basically optimal routing strategies and pricing strategies, right? So you could do something like apply IVC and like kind of like so incrementally verifiable computation, and go through kind of like yeah, a couple of hexagons and get like verifiable pricing for basically Uber rides or logistics, I guess. Yeah, and similarly, because we're interested in also blockchain applications, right? If you have the authentic location, you can do something like privacy-preserving validator geolocation with high authenticity, whilst keeping kind of like the privacy of the validator without disclosing its location, right? Which would be very cool to do, and probably also has some impacts on the MEV landscape, I guess. Right. There's also some remaining challenges and applications for floating point snarks. Our circuits are very universal. You don't have to apply this to the ZKLP or location privacy use case. You can also basically try to figure out how to do IEEE 754 compliant ZKVM operations, right? So for example, everyone's right now building ZKVM for the RISC-V instruction set architecture. So there's like the F extension in the RISC-V instruction set architecture. So you could think about basically how to apply the optimizations that we provide that are very generic in kind of like optimizing, floating point computation for ZKVMs. You can build ZKML models by adapting our implementation to half precision, so 16-bit instead of 32-bit or 64-bit. Or you can do also basically audio authentication, because digital signal processing always involves floating point computations, right? Cool. That marks the end of our talk. With our implementation, I guess you can now use floating point arithmetic in your circuits. Our implementation is in Go, specifically in GNARC. And it worked pretty well with our application. So yeah, happy to ask and answer any questions that you might have. Thank you. And sorry for being a bit over time.
Yeah, no worries. Thank you so much for the great presentation. And yeah, for the audience, feel free to ask questions in the chat and also unmute yourself to speak. Yeah, we can wait a couple of minutes, maybe 2 minutes, if there are any questions. But thank you so much, Chengru and Jens, for the presentation.
Yeah, thank you so much for having us.
Thank you. There is one question.
Yeah, you can just send me, I guess, or Chengru an email if you'd like to discuss if you've done any similar work to this one. Let me just drop my email here, the chat, that you can reach out. There you go.
Yeah, and mine is this. You can also find me via my UCL email address, but it will, I guess it will expire in September. Yeah.
Okay, then if there are no more questions, thank you very much for the presentation, and thank you everyone for attending, and have a nice day, everyone.
Thank you so much. Hope it was helpful. Have a nice day. Bye.
Bye-bye.
Thank you. Bye.
Thank you. Bye.